guys, welcome to the Mechanical Engineering Explained. Today I will be showing you how to derive the equation of motion for a single degree of freedom undamped free vibration. First, let's assuming the weightless spring one end is free and one end is fixed. So this spring is at the steady position. Now at the free end, attach a mass M. Due to the weight of the mass, spring will be stretched and deformed, delta st. After some time, weight of the mass is balanced with the spring force produced in the spring. So at the this is a static equilibrium position. So at the static equilibrium position, um, weight of the mass is equal to k delta st. After that, if I give initial stretch to the spring or compress the spring and leave, the mass will be oscillate about its equilibrium position. And to derive the equation of motion, so first we have to draw the free body diagram for this spring mass system. So mass m. So force produced in a spring is kx plus delta st, and the downward force is mg, and this one is we are measuring at its static equilibrium position. So I'm considering the downward as a x positive, so x double dot. Now we are applying the Newton's second law of the motion. So sigma f force, and I'm showing is a vector because I'm taking the downward direction is a positive, is equal to mx double dot. So all forces mg minus uh, spring forces in upward direction, so it's negative x plus delta st equal to mx double dot. So we know that at the static equilibrium position, mg is equal to k delta st. So here the mg and k delta st is cancel out. So remaining term is kx is equal to mx double dot. And if we rearrange this term is mx double dot plus kx is equal to 0. So this is the equation of motion for single degree of freedom undamped free vibration. And if we, rearranging this term, so x double dot plus k by m x equal to 0, and this the equation is exactly similar to the simple harmonic motion equation x double dot plus omega square x omega square is equal to k by m, and omega is equal to square root of k by m. So this is the natural frequency of uh, nat- um, natural frequency of the system. This one is expressed in the radian per second, and if we want in a hertz, so is the frequency f is equal to omega divided by 2 pi. So you can say 1 by 2 pi square root of k by m in a hertz, and sometimes it's denoted by omega n because it's the natural frequency. This one is the angular natural frequency. This one is no frequency in hertz. If the so this is the undamped free vibration system. So spring is or the mass is continuously oscillating for the infinite time. But in actual in a practical, there is a after certain times the mass is stopped to oscillating, and this is caused because of damping. It may be material damping or air resistance, anything. But if there is a if you want to derive the equation of motion for the uh, damped, damped, damped free vibration system, So it's the same procedure, and but the equation of motion will be mx double dot plus cx cx dot plus kx equal to 0. This is the equation of motion for the damp damp free vibration system, single degree of freedom system. Uh, so same as here, and the solution of the system, undamped free vibration system. This is the ordinary differential equation. So the possible solution will be x of t is equal to a0 cos omega n t plus phi, or you can write down a cos omega n t plus b sin omega n t, anything. Yeah, you can use any of these two equation. And so for the example, you have to give on the initial displacement or initial velocity, so you can uh, give derive, derive by like if you give the derivative of this one x dot and follow the do the derivative of this any equations and input the initial velocity, and you can derive the value of the amplitude a, and this one gives the displacement and the velocity of the mass at the any instant. So this is the equation of motions, and if you want videos on any specific topic, just comment down in below. And thank you guys.